Ever since that day, it's been money. I don't know. All right, so we left off here with conjugate acids and conjugate bases. That was the very last thing we did yesterday at the end of the class, okay? So we're going to go through some more examples of this. And essentially, with acids and conjugate bases and conjugate acids, it's just a matter of identifying what they are. And this is really going to come in handy at the tail end of class, because at the tail end of class, we're going to have to identify whether a salt compound is acidic, basic, or neutral. Yes, salts can be acidic and basic or neutral. It's kind of a thinky process, but we'll give you a couple tools to figure it out. So let's do this one. Here's a base, here's an acid. How do I know that's the acid? Hydrogen is the first element listed in the formula. How do I know this is a base? That kind of works. It's not the acid, and we're talking about acids and bases. Yeah, I like that answer a little bit. The NH2, okay? That nitrogen group right there. Okay, this is some molecule you've probably never seen before, but it has that nitrogen group. That's a dead giveaway that it's going to be a base. So let's do our acid-base reaction. Let's donate a hydrogen from the acid to the base. When I do so, I end up with this. Okay. Now, with Bronsted-Lowry, like I said yesterday, we don't get water as a product. But that's okay. These are all aqueous. All four of these are aqueous. Water is there. It's just not written as a product in our reaction. These two things are actually a salt. Okay? I mean, it's kind of a gigantic, crazy salt, because this is a huge cation and this is a huge anion. But in actuality, that is a salt. So this is an acid-base reaction, Bronsted-Lowry. We've moved one proton or one hydrogen ion. And this is the product. Now, let's identify acid-base pairs. Acid, conjugate base, base, conjugate acid. Let's identify those. So, on the left, what's the acid? What's the base? On the product side, identify their pairs. What is the conjugate base of H3PO4? What is the conjugate base of H3PO4? And if you need to look at the previous problem, it'll help quite a bit, I imagine. It's H2PO4 1-. Okay? This is the acid. After it's donated a hydrogen, what you have left over is its conjugate base. This is the base. It accepts a hydrogen. What I get after it has accepted that is the conjugate acid. Okay? That's one way of thinking about it. This is a pair. This is a pair. All right? The other way you can think about it, or if you want to try to identify whether these are acids or bases on the product side, run it backwards, right? If you look at this from right to left, one of these is donating a hydrogen to the other to get these, right? Either works. Here's the other thing to remember. A conjugate acid-base pair is different by one hydrogen. That's it. Okay. Here's this. Hey, look, it added a hydrogen. That's a pair. Here's this. Hey, look, I removed a hydrogen. It's a pair. Okay? Easy peasy. Sweet. Let's try a couple more. This one's a little funkier. This is called the autoionization of water. In other words, water reacting with itself. Okay? I have water plus water on the reactant side. And what we're going to do is we're going to do a Bronsted-Lowry acid-base reaction. Okay? So one of these waters is going to donate a hydrogen. The other water is going to accept the hydrogen. When that happens, we end up with H3O1 plus and OH1 minus. Now, as weird as this sounds, this reaction is a real thing. Okay? Water can autoionize. This reaction is rare. It happens like if you have, what is it? If you have like 100 trillion water molecules, this will happen like once. So it's rare, okay? But it happens. Yes?
Is this like a reaction that you'd be able to like tell?
Not really. I mean, now, there's methods of like measuring the fact that this has happened. Yeah, the scale of it's insanely small. Yeah. So it's very difficult for like, unless you got really good equipment, right, it would be tough to like detect that this is actually occurring. But anyway, it happens. So what I'd like you to do, let's identify the acid-base pairs. Acid conjugate base, base conjugate acid. Doesn't matter which water you pick, does it? What's the difference between that one and this one? I don't know, they look pretty similar to me. So whatever one you want to call the acid, go for it. Whatever one you want to call the base, go for it. But on the other side, it does matter. Okay? The other side does matter. Because one of those absolutely is an acid, one of those absolutely is a base. I think you'll be okay identifying that too. Okay. I'm going to call this first one my acid, second one my base, I guess. The acid will donate, the base will accept. So after the base is accepted, I get this thing. That's a conjugate acid. This is one pair. After the acid has donated the hydrogen, I'm left over with this hydroxide. That's a conjugate base. This is another pair. Okay? So, a couple other things that I want to point out. That looks very familiar, right? That's hydroxide. That's like the definition of what base is, right? Things that produce hydroxide when they're in water are bases. Have you seen this before? H3O1 plus. Maybe you have, maybe you haven't. Here's the deal. If I have acid, we normally just call acid H1 plus, right? Hydrogen ions. All this is a hydrogen ion with a water attached to it. That's it. Okay? It's called hydronium. Okay, it's called hydronium. And H3O1 plus, for all intents and purposes, is the exact same thing as H1 plus. Okay? They are equivalent for what we're up to. When you see H1 plus, you should think hydrogen ion, acid. If you see H3O1 plus, you should be thinking acid. They are the same thing. All right? You should write that down. H3O1 plus equals H1 plus. We will treat them the exact same. No matter which one shows up, we think of them the exact same way. They are acid. And H3O1 plus is called hydronium. So if you ever see it, treat it just like you would H1 plus. Think about it just like you would H1 plus. It is acid. All right. True or false? Water could be an acid or a base. True or false? Water can be an acid or a base. True. We just proved that. A fancy name for this is called amphoterism. Okay. Not that it's a weird term. You could also use a different version of the word and call water amphoteric. Okay, that's another usage of that word. It just means a substance that can either be an acid or a base. Water is not the only one. Okay, there are others. But water is the most common one that we use. So here's two more reactions. Do some Bronsted-Lowry acid-base stuff. This is water with a what? What's this substance? It's a base. How do we know it's a base? Because of the nitrogen group. So this is your base. That's your acid. Give me the products. Down here, this is HSO3 1-. It's a polyatomic ion, but that H out front means it's an acid. Here's your acid. Water is now going to behave like a base. Give me the products. Go for it. Give you 30 seconds-ish. Oh, look at that. See the bottom of this slide? Couldn't help myself. I was so concerned about making sure you knew that I jumped the gun. Acids donate, bases accept. In this first one, the water is behaving like an acid, and I will donate a hydrogen to the other molecule. Which is dimethylamine. And what I'm left with then is hydroxide. Okay? You can identify acid-base pairs. Base, acid, conjugate acid, conjugate base. Here's another tip. If you end up with hydroxide, spoiler alert, that's not going to be a conjugate acid. Is hydroxide an acid? Not so much, right? It's a base. So it better be called the conjugate base after you've analyzed and labeled things. That makes sense, I hope. Okay, let's do the bottom one. Flip-flopping the script here. This is now my acid. Water is now my base. So I'm showing an example of water as an acid. I'm showing an example of water as a base. Doesn't matter. It depends upon what else it's with. Okay? If it's with a base, it'll behave like an acid. If it's with an acid, it'll behave like a base. Just a matter of what else is there. So I transfer the hydrogen over. I end up with SO3, 2-. And remember, if you're paying attention to the charges, right? I hope you're paying attention to my charges. The hydrogen ion we're transferring is obviously 1 positive. So wherever it goes up in charge by 1. Wherever it leaves, goes down in charge by 1. Right? I'm hoping that math makes sense when I'm switching charges a little bit. And I get H3O, 1+, hydronium. Acid base. And now this is going to be my conjugate base. This is my conjugate acid. And I have pairs. Okay? I could bracket these out if I wanted to, I suppose. Sure. And there they are. Again, like it says, this is hydronium, it's H1+, it's acid. Okay? And same thing goes there, right? If hydroxide cannot be a conjugate acid, hydronium cannot be a conjugate base, right? It's literally the definition of what acid is. So same thing. Questions at all? This is easy stuff, I hope. Okay. Let's sprinkle in some fun. Acid conjugate or acid-base conjugate pair strength. Okay, here's where this is leading to. When you have a pair, an acid and its conjugate base, or a base and its conjugate acid, they are equal, or sorry, they are opposite on the strength scale. All right, what I have here is not all of the acids or bases that exist by any means. Okay, not even close. But here is the takeaway, and we'll work with this for the remainder of the hour. All right, we're looking at the relationship between an acid and its conjugate, or a base and its conjugate. If you have a strong acid, okay, these aren't all of them, but these are some of them. If you have a strong acid, its conjugate base is going to be negligible. Well, what I will say is neutral. Okay? I will use the term neutral. And when I say neutral, I'm talking about pH, meaning like a pH of 7. Okay? So I have a strong acid, HCl, very strong. Its conjugate is extremely, extremely non-basic, meaning it's neutral. Here's the here we got to be extremely careful, and I'll try my best not to do this. I warned you a week and a half ago or 2 weeks ago about like strong versus weak in chemistry. Strong and weak are not opposite. Okay, that sounds stupid to say in the English language because they're very clearly opposite in real world, like, right? But in chemistry, they're not. Strong is one extreme, neutral is the other extreme, and weak is anything in the middle. That sounds very strange, but I need you to internalize that somehow. So here's the deal. Strong, weak in the middle, neutral. Okay? So look, these are pairs across the way, right? This is an acid, that is its conjugate base. This is an acid, that is its conjugate base. You see that? The strong acids are on top, the strong bases are on bottom. Okay? So it's kind of like a push-pull relationship. If I have a strong acid, its base will be neutral. If I have a strong base, its conjugate acid will be neutral. If I have a weak acid, the conjugate base will be weak. That sounds weird, but remember, the scale is strong, neutral, all the way on the other extreme, and weak means anything in the middle. Okay? You're gonna have to fight it. Your brain's gonna fight it. Because strong and weak feel like opposites, but they are not opposites in this scale. Strong and neutral are opposites. Weak is in the middle. So, like I just said, I'll say it one more time. Strong acid, neutral conjugate base. Strong base, neutral conjugate acid. Weak acid, weak conjugate base. Weak base, weak conjugate acid. Okay? If I use different terms, it would make so much more sense. Right? Top acid, bottom base. Bottom base, top acid. Sorry, whatever. No, sorry. Top base, bottom acid. Middle base, middle acid. Right? Those words would be much more friendly. That's not the words we got. So, all of this relationship stuff with these conjugate pairs is going to lead us into trying to determine whether salts are acidic or basic. You see the table on the next page? That giant table at the bottom? That's the end goal for today. We're almost there. It doesn't look like it because I got a whole bunch of words in between now and then, but I'm going to skip over a bunch of this stuff. Or at the very least, let you just read it really quickly, and then we'll start plowing into this stuff. So, if an acid is very strong, its conjugate base is such a poor base that water is actually stronger. Okay? The conjugate base of hydrochloric acid, aka the chloride ion, strong acid, chloride as the conjugate is neutral. It's literally a worse base than water. Okay? If I have a weak acid, its conjugate base will also be weak. That's the middle ground. If I have a base that is very strong, its conjugate acid is such a poor acid that it's actually, that water is stronger, I should say. Okay? And then if I have a weak base, the conjugate acid is also weak. Remember, weak is the middle ground in this scale. Strong and neutral are the extremes. So that brings us to salts. Salts are the product of acid-base reactions. Okay, salts are produced when acids and bases react, right? We get water, we get salt. We're going to analyze the salt. And we're going to try to determine whether a salt is acidic, basic, or neutral. And the way we're going to do this is by breaking that salt into its pieces and analyzing each piece individually. So let's read these next two. These are like rhetorical questions. I don't know why I have them there, really. I'm not going to answer them. Well, we're going to answer them, but in the table. Okay? So you can ignore those. But read this paragraph, read that paragraph, and then let's jump into some of these examples and start plowing away at them and see how many we can finish before we call it a break. Okay, read the next 2 paragraphs on your own if you could. All right. Ready to have some fun identifying salts? Okay, let's do the first column together before we jump into any of the acid-base stuff. Okay, let's just look at these compounds and try to identify whether they are salts or not. Most of them are, some of them aren't. Okay, so hang with me. NaCl, is that a salt? Of course, right? That's like the poster child of salts. Barium nitrite, salt? What do you need to have a salt? Metal, nonmetal, or metal to polyatomic ion, right? Something like that. Barium nitrite, is it a salt? It is. That's a metal. That's a polyatomic ion. Perfect. Ammonia, is that a salt? Not at all. That's a whole bunch of nonmetals. That's a covalent compound. HClO4 perchloric acid, is that a salt? Nope. That's an acid. Lithium carbonate. Yep, that's a salt. There's my metal. There's my polyatomic ion. Come on, here we go. This thing. It feels like it's no. Here's the deal. This guy, that's a polyatomic ion. You can have a polyatomic ion in a nonmetal, or a polyatomic ion in another polyatomic ion to make an ionic compound. This is a salt. It's a sneaky salt, right? I think that's very, very clearly a hard one to identify because there's no metal. But it's a polyatomic ion and a nonmetal. So it works. It's actually an ionic compound. It's actually a salt. This guy. Brutal. These two are nasty. Okay? This is not a salt. Now, the hard part with this one is I haven't done this to you yet. If you remember yesterday when we were talking about nitrogenous bases, and I said look for NH3, NH2, NH, I also said look for N. Okay? This is one of those nitrogenous bases. It's just that the nitrogen group doesn't have any hydrogens on it. Okay? But this is more closely related to ammonia than any of the ionic compounds. Don't worry, I'm being mean on the note sheet. I won't be this mean on the text. Okay? I'm getting all my meanness out before Christmas, just like the Grinch. And then I come full circle and I'm really nice. And I give everyone's presents back. Or something. What's your favorite Grinch, by the way? Like the original animated one from way back in the day? Like I'm talking the old one.
Yeah. You like
Which new one? There's more than one new one.
like the movie, like not the new animated one, but like the middle, the like realistic.
With Jim Carrey?
Those
Yeah.
are scary.
I do like that one.
Those ones are too scary.
The one with Jim Carrey is great. I think he's, I don't know, I think he just nails it. Yeah, it's a long movie, but I don't know. I think he's like, and he's really funny. He's really good in that movie. Okay, anyway, I don't know what I'm talking about. Salt or not salt? That's salt. Metal, polyatomic ion. Salt or not salt?
I want to say no.
What is this?
Oh, shoot.
That's a polyatomic ion. What's that? That's a polyatomic ion. It's salt. This one, 2 polyatomic ions. Both the last ones here are polyatomic ion. All 4 of those are on your list from the bottom 2. All right, so we've gone through and we've identified whether they are salt or not salt. Let's go to the 3 not salts first, because I think those are easier to answer, and that's not really why I'm doing this stuff. Answering the questions about the salts is what I really care about today. Okay, so let's do this. Is part of this molecule acidic? No, it's a base. Is part of it basic? Yeah, it's a base. So what is it? It's a base. Okay, cool. Is part of this molecule acidic? Yes, it's an acid. Is part of it basic? No, it's an acid. Is part of this molecule acidic? No, it's a base. This is a nitrogenous base, this C2H53N. Okay? That's a sneaky nitrogenous base. So no, it's not acidic. Yes, it is basic, and yes, it's a base. Okay. Now, these questions aren't really relevant for acids and bases like these 3 examples. These questions are what we're going to answer about the rest of these salts. The goal is hopefully to look at the salt and analyze it and figure out whether this salt is acidic, or this salt is basic, or this salt is neutral. That's the goal. Here's how we do that. Okay, let's take our first salt here. And I'm going to scroll down. I think you got a smidge of room on the bottom of the paper, maybe? Not a lot. How's the backside look? All right, that's good. You don't need it right away, but we might need the backside in a little bit. Come on. All right, so the first salt is sodium chloride. When you read those 2 paragraphs, it said something along the lines like this. The cation comes from a base. Okay, when acids and bases react, you make salt. The salt you make is 2 pieces, cation and anion. The cation of your salt came from the base. The anion of your salt came from the acid. Okay? So let's analyze this salt by looking at its pieces. This salt is comprised of sodium ions and chloride ions. Okay? This sodium is the conjugate acid coming from a base. This chloride is the conjugate base coming from some acid. The way we look at this now is, what base would sodium have come from? What base would have given us sodium ions? Sodium hydroxide. Yeah. And sodium hydroxide is strong. So therefore, this being the conjugate of that should be neutral. In other words, not going to mess with the pH at all. Let's look at the other side. Chloride. What acid would have given us chloride ions? HCl. HCl is strong. Therefore, the chloride ion as its conjugate would be neutral. So, let's go back to the top. That is the correct thinking. Now let's put that in motion a little bit, okay? The acidic part, what we're looking at here, is we are looking at the cation. The basic part, we're looking at the anion. Not always, but that'll help a little bit if you write those above the column. Okay, it's not perfect. Sometimes that breaks apart, and I'll show you where it breaks apart later. But generally, we're looking at the cation for acidity and the anion for basicity. I don't think that's a word, but the basic character of it. All right. So we analyze this. We looked at the sodium. The sodium came from a base, therefore it's a conjugate acid. The base it came from was sodium hydroxide. Sodium hydroxide is strong. The sodium ion as its conjugate, therefore, then, is neutral. Is part of it acidic? Is the cation acidic? No, it's not. Sodium is not acidic because it's the conjugate of a strong base. Is part of this salt basic? We look at the anion. Chloride came from HCl. HCl is strong, therefore the chloride ion is neutral. So, part of it is not basic either. The cation is not acidic. The anion isn't basic. What is it? It's neutral. If you dissolve salt in water, sodium chloride in water, the pH is 7. The sodium ions and the chloride ions do not mess with the pH. They're both neutral ions. And they're neutral because their partners or their pairs, their conjugate pairs, are strong. Let's do another one. Barium nitrite. Okay. Barium nitrite is comprised of a cation, barium 2+, and an anion, nitrite, 1-. The cation comes from the base. What base would have given us barium ions? Barium hydroxide, strong or weak? Might have to think about that. Barium hydroxide. Barium comes from column 2 with hydroxide. Any element from column 1 or 2 with hydroxide is strong. So barium hydroxide is strong. What does that tell us about the barium ion? It's neutral. Oops, I'm sorry. Can't do that. The cation is neutral. Let's look at nitrite. What acid would nitrite have come from? You don't know the name of that probably, but all you have to do is put an H on the front of it. Okay, that's nitrous acid. Nitrous acid. Strong or weak? Double check your subscript. Nitric acid is strong. That's HNO3. Nitrous acid is weak. That's HNO2. Yeah, very subtle, but it matters a lot. So nitrous acid is weak, somewhere in the middle. Remember, weak means middle. Therefore, the conjugate base of that, which is nitrite, is it's weak. Again, if one thing is weak, its conjugate is also weak. That's the middle ground. Weak substance, weak conjugate. What that means is that this absolutely has basic properties. Nitrite ions will mess with the pH. They will change the pH. They will actually raise the pH because these are bases, or they have basic properties, you can call it. All right, let me go back up. And this part is basic. And overall then, my salt is basic. If I were to take barium nitrite and dissolve it in water and check the pH would be greater than 7. And it has everything to do with the relationship of conjugate acid-base pairs. Let me recap, because I can start losing you really quickly with this concept, right? It gets confusing. Barium came from barium hydroxide. Barium hydroxide is a strong base. Nitrite came from nitrous acid. That's a weak acid. Okay? When your ion comes from a strong substance, the ion as the conjugate of that is neutral. If your ion comes from a weak substance, the ion as the conjugate is also weak, meaning it does have some basic or acidic properties depending upon which piece you're looking at. Are there questions? Try one on your lonesome. Take a look at lithium carbonate and try to determine whether that would be acidic or basic. What you do, you break it into its pieces and analyze the relationship between the ion and its conjugate. If it comes from a strong substance, the ion is neutral. If it comes from a weak substance, the ion is also weak, meaning it does have acidic or basic properties. Give it a shot. Try to confidently answer that if you could. And this is absolutely something you guys need to try. If you watch me do this and then go to your homework, it's not going to make any sense. You have to do this mental hurdle. You have to be the one that needs to think about this and commit to an answer. And if you commit to an answer and it's wrong, well, then you're going to learn something and we'll figure it out the next one, right? But if you just watch me circle all these bubbles and then go try your homework, I don't think it's going to go well unless you've done the mental hurdle yourself. And if you're good on lithium carbonate, you're welcome to try a couple others. You can kind of, again, we got like 5 more to go through here. You can kind of go through the list. It's up to you. If you're feeling confident. And if you got a good eraser, just in case. Might not need it, but you never know. It's always good to have a nice eraser nearby. Lithium would come from which base? Which base? Throw a hydroxide on it. Lithium hydroxide, right? Strong or weak? Therefore, the lithium ion is neutral. It came from a strong base. Lithium is the conjugate acid of that strong base. Base, conjugate acid, neutral. So the lithium ions aren't going to mess with our pH. They're neutral. How about carbonate? Carbonate comes from which acid? Yeah, I don't think you know this, do you? Yeah, add some H's, right? Now we got to add 2 H's in this instance because it's 2 minus. But it's going to be that, because I have a 2 minus charge on my carbonate, so I need 2 hydrogens out front to counterbalance that with charges, right? This is called carbonic acid, okay? You don't really need to know that. But is it strong or is it weak? Why is it weak? How do you know that? Yes, exactly. As dumb as that answer sounds, right? Like, why is it weak? Well, because it's not one of the 6 I'm supposed to know. Yeah, that's what I want you to think. That's how I want you to approach it. It sounds like kind of a cop-out, but that's okay. You need to know your 6 strong acids. If it's not one of those 6, it's weak. So yes, that's exactly what I wanted you guys to say. This is a weak acid. If it's a weak acid, the conjugate, therefore, is a weak base. And it's going to mess with the pH. It has basic properties. And overall, then, I look at this salt. It's a salt. I analyze both pieces. The cation was not acidic. The anion was basic. And overall, it's basic. Now, I told you earlier, this unit, that all carbonates are bases. Remember that? Okay. We didn't analyze carbonates in this way But even by doing this analysis, what I told you earlier is still true, right? We're looking at it a little more in depth or at a different way of kind of thinking about it. Okay. How about this guy? Now we're getting funky. I can't just slap OH on this, can I? No, I can't. This is a nitrogenous base. This is one of those bases, or I should say, sorry, this part comes from a nitrogenous base. I should say it that way. All right. Ooh, I'm gonna trip again. Scoot over, step. What I have, hold on, what was it? Methylamine, okay. This is the salt compound, right? Let's break it into its parts. I have a giant cation, and I have a simple anion, I1 minus. Now, this came from what? If you look back at the previous examples, it might help. Okay, we've done things like this. We did things like this today. Look at this top one right here that we reacted with water. Okay, this is like the piece that would be a part of the salt. Okay, this chunk right here, this is what it would have come from. So this is the piece. What base would that have come from? When you have these funky nitrogen compounds, okay, when you have these funky nitrogen compounds, if it has one positive charge, that's the conjugate acid of it. If it's neutral, that's the base. It's the exact same thing as ammonium and ammonia. Ammonia is NH3. That's a base. Ammonium is NH4 1 plus. That's the conjugate acid. This CH3-2NH is neutral. That's the base. CH3-2NH2 with a 1 plus charge is the conjugate acid. CH3NH3 1 plus is the conjugate acid. It would have come from CH3NH2, the base. Now, that's all well and good. I'm giving you more than you need there. Did it come from a strong base or a weak base? Weak. Those are all weak. Every single one of those nitrogenous bases are weak bases. If this came from a weak base, what is this then? Also weak. It's a weak acid. So is my cation acidic? Yes, it is. I go to the anion. That's iodide. What acid did iodide come from? Hydriodic acid. Strong or weak? If hydriodic acid is strong, what does that tell us about iodine? Neutral. And overall, then, my salt is acidic. Yeah. Yeah. Sodium sulfite. Sodium comes from what? Yes, Jay. Yep, yep.
Can you just work backwards and do like the I first? If it's does not have part basic, then you would have just used that others part acidic.
Not necessarily. They can both be yes and they can both be no. And if they're both no, it could be a neutral salt like this one was. Yeah, we're getting there. It makes it worse, by the way. Or better. I don't know. Your choice. Sodium comes from what? What base did that come from? Sodium hydroxide, strong or weak? Therefore, sodium is neutral. Doesn't mess with the pH. Sulfite comes from an acid you don't know. But if we slap some H's on there, because sulfite is 2 minus, by the way, it's sulfurous acid. Strong or weak? Yes, this is another one we got to be careful with, right? I did nitrous acid to you earlier, HNO2. Not to be confused with nitric acid, which is HNO3. This is sulfurous acid, H2SO3, not to be confused with sulfuric acid, H2SO4. This, if you slap some H's on there, is a weak acid. Therefore, sulfite is, as its conjugate, a weak base and will mess with the pH, and I do get a basic salt. Now we've arrived at the fun stuff. The good news is I'm going to gloss over it because we don't have all the tools in our toolkit yet to do this. Okay, so I'm not going to give you the full fun in Unit 4. We'll give you the full fun when we get to Unit 7. Salts will come back later this year in the spring. Okay, but let's just analyze these from what we know so far and see where it ends up. Ammonium cyanide. Ammonium came from which base? Ammonium. Strong or weak? Therefore, ammonium is, and it's going to mess with pH. Cyanide came from hydrocyanic acid. If you put an H on there, HCN, that's called hydrocyanic acid. Okay, do I think you should know that? Maybe. I don't know. Not a big deal. Is it one of your 6? No. So this came from a weak acid. Therefore, the cyanide as its conjugate is a weak base. And it's going to mess with pH. So I have an acidic chunk. I have a basic chunk. And overall, it is how acidic is that? How basic is that? Is one of them more acidic or basic than the other? Maybe. There's a way to answer it, but we don't have all the tools we need. So for now, we're just going to leave it, because otherwise I'd have to teach you like a whole other day's worth of stuff in order for you to understand it. So we're going to just leave it. The thing we cannot do is call this neutral. Okay? Let me say that in a different way. We can't assume that it's neutral. There's varying strengths of acids and bases, right? They're not all created equal. So just because I'm saying this is acidic and just because I'm saying that's basic doesn't mean that those parts cancel each other out. They might, they could, but they might not. And we have to look a little deeper. And again, I'd have to teach you a whole day's worth of stuff to answer that at the moment. So we'll teach that whole day's worth of stuff in March, and then we'll give you the answer. But the 3-month cliffhanger, exciting. How can you even go on break now? You just like, man, she's gonna eat away at you for like 3 months. This is crazy. Huh? Oh, it might though. You're gonna wake up in a hot sweat tonight, like what is it? Okay, all jokes aside. Anyway, so this one, same thing. If you've looked at this, right? Maybe you have, maybe you've worked ahead of me. This ammonium came from a weak base, therefore it does have acidic properties. This acetate came from a weak acid, therefore it has basic properties. And overall, it's, I don't know. I mean, I know, but we'd have to think about it. We have to analyze it, and that's the difference. Okay, so the bottom 2 you can just leave. I don't give you any of those naughty ones on the homework assignment. And we've reached the point where I'm done with 4.8. I kind of apologize for keeping you this long today and all that good stuff, but whatever, too late for that. Have a lovely break for those of you at home. I sincerely hope you get some rest and can enjoy some time with your family. Yeah, you know, take naps and all that good stuff and eat good food. Sounds nice. So have a lovely break, guys. We will catch you afterwards.
Yes.